All right, welcome back to BME 2315. In this lecture, we're going to be looking at how to solve systems of equations for their unknowns using Gaussian elimination. So as we discussed last time, linear equations are used to model all sorts of different biomedical systems, whether that's in biomechanics, where we have linear systems of the form F equals ma, in bioelectricity, where we've got conservation equations that are cast in the form of V equals IR. In blood flow through vessels, we have equations that relate the pressure to the volumetric flow to resistances in those vessels, and even in mass transport, where we have diffusion constants or diffusion gradients, such as the difference in concentration in two compartments that is driving the flow between these compartments divided by some permeability constant. So all of these can be cast in terms of a linear equation, ax equals b, that we then need to solve. And so today's lecture is learning about how we solve that using Gaussian elimination. So to give you a biological focus for the problem set, in problem set 5, we're going to be modeling how blood flows through this little resistance network. And specifically, under normal circumstances, blood flows in through both sides to go out the central vein. However, experimentally, the Price lab found that when they ligate this artery, that means tie it off, then it can redirect blood flow to go through a different path than it would otherwise. And so we're going to look at how you can predict those sort of changes in a computational model. Basically, all this model is a set of algebraic equations with Q's that are the variables that are unknown, and R's are the resistances for each of these blood vessels. And if you know about the physics, we won't get into that here, but you can use that to write down the conservation equations that show that the flow in and out of the system, and you can come up with this equation right here. And so in the problem set, you'll be using Gaussian elimination to actually solve for all these unknowns. So let's look at the different ways that you know of solving unknowns in algebraic systems. Well, one of the approaches is to use a graphical approach. So, for example, if you have two equations, you could plot them out. Equation 1, equation 2. And in this case, if you do that carefully, more carefully than I've done here, you could find that the intersection is at 1.25. So that would mean that the solution is x1 equals 1, x2 equals 2.5. So that's a fine approach if you're only dealing with two equations and you're dealing with something quite simple. But the whole point of using computational methods is that it allows you to tackle much larger systems that are more realistic than this. It allows you to go beyond what you can do by pen and paper. So we're going to need something else. The other approaches that you may have seen are algebraic strategies. For example, one of them is to solve an equation for one of the variables, like x2 right here, and then substitute that into equation 1. That can be an effective strategy. Another approach is to add two equations to eliminate variables. So, for example, if you had these two equations, if you add them together, you could eliminate the first term. That would isolate x2, and then you can use a substituting approach. Or sometimes, if they don't cancel out right away, you can multiply equations by factors. For example, multiplying this equation 2 by -2 would put it in a form that would allow you to eliminate the variables afterwards. So there are a variety of algebraic strategies for isolating the variables. So let's take a look at how you would typically solve for the unknowns using these types of approaches. So as you've seen before, perhaps one step would be to multiply the second equation by -2. And so we're going to do that. We're going to make equation 2 prime is going to be -2 times equation 2. Okay. So the first equation is going to be unaffected, 3x1 plus 2x2 equals 8. And then the second equation becomes -3x1 plus 2x2 equals 2. Okay, so that's closer. Now what we can do is we can make a second transformation and say equation 2 double prime is the same as what equation 2 prime was, but we're going to add it. We're going to add in equation 1. Okay, so again, we're still not changing equation 1. That's still 3x1 plus 2x2 equals 8. But now this second equation has simplified like this. And so we can now solve for x2. And so when we do that, we get x2 equals 10 over 4 equals 2.5. Okay, now with x2, we can substitute x2 into equation 1, right? And we get, so equation 1 was 3x1 plus 2, and then this is where we put in x2, this is 2.5 equals 8, and now we can solve for x1. Where x1 will now be given as 8 minus 2 times 2.5 over 3 equals 1. Great. So overall, we found that x1 equals 1 and x2 equals 2.5. So that is an approach that is complementary to the graphical approach and is somewhat better scaled, but it still requires us to kind of make ad hoc choices about what transformations we're going to be making at each time. And this also doesn't really scale very well to many equations, although you could do 2 or 3 equations like this. So as a improvement on this, as something more systematic, we're going to be learning about Gaussian elimination. And so here's the general idea is that Gaussian elimination is a method to solve for the unknown x's, even in a large system, when there are like many unknowns in that system. And so the basic strategy is that you start with your original matrices A and B in an augmented matrix form, and then you're going to use forward elimination to systematically eliminate the things in this triangle. And then, so we're going to try to get all zeros down here in this triangle. And then once we do that, then it's going to be easy for us to use back substitution to systematically solve for the last variable and then plug the answer into the next one and eventually solve for x3, x2, and then x1. So that's called back substitution. So again, it's augmented matrices. Then we're going to be doing forward elimination to try to, and the purpose of that is to try to get zeros down here in the lower triangle, and then back substitution. So let's look at how this works. How can we do this? So the first thing is to note the augmented matrix. So that would take, we've got an equation, a system of equations written right here, and when we cast it in matrix form, we have these this A matrix right here, and we have X is our unknowns, and then B, the B matrix. Okay, And so Gaussian elimination, we're going to create an augmented matrix that's A with B kind of attached to it right here. And so Gaussian elimination steps, the reason why we're augmenting the matrix or combining them is because we're going to be applying the same operations to everything in this row, not just to the A's. Okay. So let's now look at how we do so that's augmented matrix. So let's now look at how we do forward elimination. The basic idea here is that, remember, we're trying to get rid of these values. We want zeros on here in this first column after this first value. And so to do that, we're going to identify the first in round one. Sorry, my mouse went slow and then it made my drawing strange. Okay, we're going to identify the pivot value. The pivot value is the value that we do not want to get to 0. We're kind of rotating things around it. Okay, so on round one elimination, the pivot value is A11. Okay, and this first row is going to be called our pivot row. And so we're going to be using values from it in order to calculate how to manipulate the subsequent rows. So the basic idea here is that let me move this. Okay, so to eliminate x1 from equations 2 to n, that's our goal. And so we're going to apply this equation to row 2, where it said we're going to have a new version of row 2 that's given by the previous version minus this ratio, where this is the pivot coefficient. Note. Okay, and then in row 3, we're going to apply the same idea where we're updating row 3 based on the previous or the current values of row 1 divided by the pivot coefficient. And for n, so this could be for any number of rows, you would have this general equation for how you perform the forward elimination in Gaussian elimination on this first round. So to say that generally on the ith row is given by the previous value of that row minus this ratio times row 1, because row 1 is our pivot row. Okay, so let's take a look at an example of how we actually apply that. That might make it easier to see how this works. So the first thing that we want to do is create an augmented matrix. Okay, and so we're just going to take our existing system, and it says 2 minus 1, 6, 8, and then the right hand side is minus 18 and 40. Okay, and then what we're really going to need is to pay attention to this is the pivot coefficient. Right here, and this is the pivot row. So that means that we're not going to make changes to this row, but we're going to modify the other row based on the pivot row. Okay, and so what we're going to do here is, first off, I'm going to write down the existing row 1, because that's not going to change, and then we're going to apply this equation on what's left. So So we're going to start with -1 because that was the original value, minus the A1 value. So this is the AI1. So that's the A2 one, which is this position right here. So that's why we're multiplying that, and we divide by our pivot coefficient. And then in the next one, it's 8 minus -1 over 2 multiplied by -6, because that's the corresponding value up in row 1, our pivot row. And then finally, we had 40, and we're going to modify that by -1 over 2 times -18. Okay? And then if we multiply all those out, you get 2 minus 6 minus 18, 0, 5, and 31. So there we go. We can see that this was successful because this first value went to 0, and now we're in better shape. So the next aspect would be to do back substitution to solve for this last piece. But we're actually, before we do back substitution, we're going to look at how to do forward elimination on larger systems. So in round 2, so after we do round 1, then in round 2, the goal is to eliminate x2 from equations 3 to n, where n could be as many that we've got. And so we're going to kind of move. We already have a 0 here, and or a 0 in all these spots from the first round of elimination, and we're going to move the pivot to be the A22 position. Okay, and so this is now our pivot row. Okay, and so then if we write out these equations, we mark a second prime as being like the second version of this row. So the first version came from the first round of elimination, and the second is coming from this second round of elimination. And so we're updating here by the previous value of that row minus, and this is our new pivot coefficient, and this is the leading value right here. This is the leading value in the row that we're talking about, row 3. And so on the nth row, we would have the following equation. Notice that we're still subtracting off we're starting with the original value, and then we're modifying it by some product of row 2, which is our pivot row. And so for in general, for any row I, then that's given by row I is prime, so it's previous value, and then you've got a ratio of the pivot coefficient, the pivot row, and the I is the I2, which is the second column. So that's the leading coefficient there. So in general, after the second round, you may need to do up to you can continue this process as many times as you've got rows, and so you keep going up until you've isolated just one equation right here. And so once you've done that, you've got zeros right here. And so this is the general equation for round K of forward elimination, is that for whatever round you're on, it's the previous value minus the leading value divided by the pivot coefficient multiplied by your pivot row here. Let me just re-emphasize that, the pivot coefficient. Okay, so that's can be confusing to look at those plots, and so what we're going to do now is do an example of a 3x3 matrix, so you can see how that gets applied in a little bit more complicated scenario. Basically, in round one, our pivot coefficient A11 is 4. Okay, and so I'm going to write out our first equation. 4, 1, minus 1, minus 2. And then we know that in forward elimination, these leading values are always going to be zeros, so we don't really need to calculate them. And I find it helpful to write out here in terms of a shorthand notation to help me keep track of the leading value divided by the pivot coefficient. So it helps me keep track of my terms. So we're going to take right here is the previous value was 1, and so we're going to do 1 minus this ratio multiplied by what was up here above, which is 1. And then next we've got its previous value is 2 minus, again, this ratio 5/4 times minus 1, which is what right above it. And then in this position we had a 4 minus 5/4 times what's right up above it, which is minus 2. Okay, and then let's apply this to the third row. So it's a 0 again, and its original value was 1. So we're going to do 1 minus 6/4. Remember the 6 is happening because that was the previous value of the leading coefficient right here. And then we're going to be multiplying by what's in the pivot row, which is 1. We have for this third column, we've got 1 minus 6/4. So you notice this pattern right here. And then as multiplied by -1, because that's the value in the pivot row. And then finally, in the third slot, we've got 6 minus 6/4, because its original value was 6, and then we're subtracting, and then we multiply by this term out here, 6/4 times minus 2, which is the value from the pivot row. Okay, and so if we multiply all those out, you should get something like 4, 1, minus 1, 2, 0, -0.25, 3.25, and 6.5. And finally we have 0, -0.5, 2.5, and 9. Okay, so we just survived round 1 of forward elimination, and so now we need to change our pivot coefficient and apply round 2 for elimination. So in round 2, our pivot coefficient is A22 equals -0.25. Okay, so I'll write these out again. 4, 1, minus 1 minus 2. We don't have to apply elimination on this round again, remember, because we're already done with this one. So this is negative 0.25, 3.25, 6.5. Okay. And then now, because we're on round 2, these are going to be 0. Both of these are going to be 0. And so we only have to apply this formula to the third column and onwards. So we're going to start by its previous value, which is 2.5, as we see up here. So it's 2.5. I find it helpful to to do this notation where we put the leading value, which was negative 0.5, divided by the pivot coefficient, which is negative 0.25. And that's just like a little notation because we're going to be applying that across the whole row. And so we got 2.5 minus negative 0.5 over 0.25 times 3.25, because that's the value from the pivot row. And then down here we've got 9, that's the current value, minus the same fraction times the amount that's in the pivot row, which is 6.5. Okay, and so when you multiply those through, these aren't changing. You multiply these through, you'll get 0, 0, of course, negative 4, and negative 4. Okay, so we've applied 2 rounds of forward elimination and successfully got a triangle of zeros down here in the corner. Okay, so that's forward elimination. Then the next step is back substitution. And the basic idea here is that we are applying this first to x3, and then we've got these equations that help us solve for what's left, and go x3, x2, x1, and so forth. So in general, this general equation for this is that the last value of the variable is given by this equation right here. Remember that this is just an annotation for a round number. Okay, and then the other equations so subsequently we have these. So this is basically just rearranging a linear equation to say that x is given by these terms right here. Okay, so let's see how to implement Gaussian elimination's backward elimination by example, because that's probably more intuitive than just looking at these equations alone. So if we start back at the same 2 equation system that we had before, after we see this is what we had after forward elimination, we had gotten down to this matrix, and now we need to back up from it to solve for the individual variables. So n equals 2, and so we start by solving for x2. Okay, so that last equation is 5x2 equals 31. And we can rearrange that to say x2 is 31 over 5, which is 6.2. Now we're going to plug that into our next equation. So our next equation, the top one, is 2x1 minus 6 times 6.2 equals negative 18. Okay, because it's the top equation from after our forward elimination. And so that we're going to rearrange so that x1 was negative 18 minus negative 6.2 divided by 2, because 2 was our coefficient out front, and then that gives us 9.6. And so this tells us that our solution equals 9.6 and 6.2. Okay, so that was not too bad. Let's take a look at another example. So this is the 3 equation system that we had done, and this was the result from the forward elimination, and we're going to use the same basic strategy to back calculate the different x values. So first off, note that this is a n equals 3 system, and x3 equals right here negative 4 over negative 4 equals 1. Okay, so now we're going to, that was row 3. Now we're going to go back to row 2, and we look at this equation, and that equation says negative 0.25 x2 plus 3.25, and then this is where we're going to plug in our x3, which is 1, equals 6.5, and we're going to rearrange this equation for x2. So x2 equals 6.5 minus 3.25 times 1 over negative 2.5, or negative 0.25 rather, equals negative 13. Okay, so that's good. So we did row 3, we did row 2, and now we're going to do row 1. Same idea. So we're going to write out the equation right here, but plug in the ones that we know. So we don't know x1 yet, but you do know 1 times negative 13. That was x2. Okay, minus 1 times 1, which was our x3, equals negative 2. And we're going to rearrange this for x1. We find that x1 equals negative 2 minus 1, negative 3, minus negative 1 times 1, and we're going to divide by the coefficient in front of the x1, which is 4. That gives us 3. So that tells us that our x vector is 3, negative 13, and 1. Okay, so we solved it. So that's how you do back calculations. One thing that might help when you're implementing your own code for Gaussian elimination is to look at some pseudocode that gives you the rough idea of roughly what steps are involved. And so in this pseudocode, this is written not in any particular language, but it gives you the rough idea of the steps and the sequences that you might use. This is the forward elimination. And this is the code for backward elimination. And the basic idea here is that there are multiple for loops that loop down through the rows as they're needed. So in your problem set, you're going to be implementing your own version of something like this in Python. Okay, so the key points from today's lesson are that mathematical models of biological systems can be represented as linear systems, that we can express these linear systems in matrix form, often with something like AX equals B. And finally, we've been focusing today on Gaussian elimination, and this is a method for solving for the unknowns in a linear system. And the basic idea is that we eliminate variables through forward elimination, and then we use back substitution to solve for the unknown variables. Hope this was useful to you, and I'll see you next time.